Hello students, today we're going to cover section 6.5, conditions for rhombuses, rectangles, and squares. By the end of today's lesson, you should be able to determine if a parallelogram is a rhombus or rectangle. Since a square is both a rhombus and a rectangle, these properties can be used to determine if a parallelogram is a square. Our first theorem helps us to determine if a parallelogram is a rhombus. It states that if the diagonals of a parallelogram are perpendicular to each other, then the parallelogram must be a rhombus. So let's look at a proof of this theorem. I will complete this proof as a two-column proof, so I'll have statements and reasons. Our first two statements will be the given information. The fact that ABCD is a parallelogram gives us one important fact. And that is that the diagonals of a parallelogram bisect each other. In other words, segment AE is congruent to segment EC, and segment BE is congruent to segment ED. If we then mark our diagram with the fact that AC is perpendicular to BD, we can see that triangle AEB is congruent to triangle AED by side angle side. This then leads to segment AB being congruent to segment AD by CPCTC. Since opposite sides of a parallelogram are congruent, we can now say that segment AD is congruent to segment BC, and segment CD is congruent to segment AB. Now, by transitivity, all the sides are congruent, and therefore ABCD must be a rhombus. Our second theorem gives us another way to determine whether or not a parallelogram is a rhombus. It states that if one diagonal of a parallelogram bisects a pair of opposite angles, then the parallelogram must be a rhombus. And our final theorem of the lesson gives us a way to determine if a parallelogram is a rectangle. It states that if the diagonals of a parallelogram are congruent, then the parallelogram must be a rectangle. So let's look at our first problem, identifying special parallelograms. The question says a parallelogram has angle measures of 20, 160, 20, and 160, and asks if we can conclude that it is a rhombus, rectangle, or square. In this case, it should be obvious that we can eliminate rectangle and square, because the only way it could be a rectangle or a square is if it had 90-degree angles. Based on the previous theorems, we know two ways to determine if a parallelogram is a rhombus. The first way is if the diagonals of a parallelogram are perpendicular, which we do not know for certain in this case. The second way is if a diagonal bisects a pair of opposite angles, which we also do not know in this situation. Therefore, the only thing that we can say is this could be a rhombus, but we cannot determine for sure. The second type of problem that we might run into is using properties of special parallelograms to determine what value of a variable will cause a parallelogram to be a rectangle. In this situation, knowing that this is a parallelogram tells us that the diagonals must bisect each other. In order for this to be a rectangle, the diagonals must be of equal length, so it's safe to determine that all of the portions of the diagonals must be congruent. Since the portions are congruent, we can set them equal to each other and solve. So in this case, 5y plus 3 would have to equal 7y minus 5. If we subtract 5y from both sides of this equation, we get 2y minus 5 equals 3. Add 5 to both sides, we get 2y equals 8. And therefore, y must equal 4. When y equals 4, this parallelogram will be a rectangle. Our final problem gives us a real-world application for what we've been doing so far today. It says builders use properties of diagonals to square up rectangular shapes like building frames and playing field boundaries. If we're on a volunteer building team and we're trying to help lay out a rectangular patio for a youth center, how could we use rope to locate the corners? In this case, in order for this patio to be a rectangle, we know that it first must be a parallelogram. So we have to force the diagonals to bisect each other. We can do that by forcing the ropes to cut each other in half. So we could locate the center of each rope and mark it with a small black mark from a magic marker, for instance. If then we force the two ropes to cross at their centers, we would have the diagonals bisecting each other, thus forcing it to be a parallelogram. To force it to be a rectangle, all we must do is force both ropes to be the same length. So the final question asks, how could we make this a square? In order to force this to be a square, it would have to be both a rectangle and a rhombus. We already have a rectangle, so in order to force this to be a square, all we have to do is confirm that we can force this into being a rhombus. In order to force this rectangle to be a rhombus, all we have to do is force the diagonals to intersect each other at a 90-degree angle. If we do that, then we'll have a square patio. That concludes the video lesson for section 6.5, Conditions for Rhombuses, Rectangles, and Squares. With the information you have, you can now determine if a parallelogram is a rhombus or rectangle. Please don't forget, if it's both a rhombus and a rectangle, the most accurate classification is a square. Please don't forget to take the quiz, and I'll see you soon.